So, in this example that we are considering, so to this 8051 port 3.3, this pulse generator is connected, and on 1.3 line we have got the LED. Now, so this this ORG 000 hex, so you know that this is the instruction, this is for an assembler directive that tells the assembler that this assembly process should put the code from this address onwards. So, at the location 000 hex, so if you look into this memory map, so what we do at this position, this is the address 0000. So, there we are putting the instruction LJMP main. So, this is the instruction LJMP main that is put here. So, your main is located, so your main program will start from 30 hex onwards. So, this is the 30 hex, this point onwards the main program will be loaded. So, there I have got this set B tcon 2. So, this is there. So, this is the set B instruction is there. So, when the processor will start, it will find this LJMP and it will come to this 30 hex is a point, and from that point it will start executing. So, apart from that, so we have said that it is connected to the external interrupt INT1. Okay. Now in INT1, so we need to find out what is the interrupt address of this INT1. So, INT1 is 0013. So, this is the vector address. So, I have to put the corresponding ISR in the we have to put the corresponding ISR in the vector address 13. So, this is done here. So, this is my interrupt service routine. In the interrupt service routine, what I will do? I will be glowing this LED on. I will be glowing this LED on, and accordingly I will be turning it on. I will wait for some delay, and then I will be turning off the LED. So, whenever this interrupt will occur from this source, I will glow this, I will put a 1 here, so that the LED is turned on, wait for 255 cycles by this small delay loop, the software delay loop is there, which will be putting a delay, then I will turn off the LED and then it will return. So, how this whole thing is done is that you see we are so in the main program what we are doing, we are making this set B tcon point tcon.2. So, tcon.2 it will make this INT1 edge triggered. So, tcon register, so we had got that interrupt types, okay, that so the type is set to 2, type is set to edge triggering by setting that bit to 1, and this interrupt enable register. So, we are enabling the interrupts like EA bit is set to 1. So, this is this part is setting that EA bit. So, this is setting of that EA bit, and this is the enabling of the external interrupt. So, rest of the interrupts are disabled. So, in the main program we just select the type of this interrupt 1, and we select and we enable the interrupt 1 line, and then we are the main program it waits in an infinite loop SJMP here, because the main program has got nothing more to do. Whereas, now the timer has been enabled. So, from the outside world these pulses will be generated, and whenever this edge triggering will occur, low to high transition will occur. So, this will be the processor will get an interrupt. On getting this interrupt, this ISR will be since it is an INT1. So, processor will automatically jump to the address 0013. So, 0013 is somewhere here. So, this is the address 0013. So, there actually I will have all this instruction, that set B P3 P1.3. So, this instruction will be there. So, it will be starting from this point. So, there it will be executing this, as a result this LED will be turned on, it will wait for some delay here, and then the LED will be turned off, and then it will be returning from interrupt again. So, it will be returning to this point only, it is the main program will continue waiting here. Then after some time again the next falling edge will come, and again the system will get another interrupt, and when it gets another interrupt, again the same the interrupt service routine will be invoked. So, it will come to this point. it will continue from that point onwards. So, this way this interrupt service routines, external interrupt service routines can be interrupt sources can be integrated with the system, and we can have the service routines for them for getting various jobs done. Okay. So, next we will look into the serial communication. So, in case of 8085 we have seen the serial communication. So, in case of 8051 also serial communication is possible, and we will see that how this is done, like so there is a there are some dedicated pins for that purpose as well. So, how to do the serial communication in 8051. So, just to recapitulate, so we have got this basic serial communication modes like simplex, half duplex and full duplex. In simplex mode, the transmission is in one direction from transmitter to receiver. In case of half duplex, so this transmission can be in both the direction, but at one point of time transmission is in one direction only. So, when it is connected, so once so there is it is shown by these switches. Once this connection is established, so it will this transmitter to receiver. After some time, the direction will be reversed, and now it will be transmitter to receiver. So, it can be both way, but at one point of time only one direction the information will flow. On the other hand, in case of full duplex, we have separate transmission and receiving lines. So, transmission can take place in both the directions simultaneously. So, that is a full duplex type of communication. So, when there is any serial communications, they follow this type of protocol, that when no communication is taking place, so there is we are the signal line is high, and then we have got when the transmission starts, the first we send a low bit. So, that is called that is the low bit is there. So, that is the LSB, and then after that the bits are transmitted. So, in this diagram, so this start bit is the low bit, and that is the start of the transmission, and then we are sending the 8 bit of data D0 to D7, and then one or more stop bits may be set. And we have some bits per second, the BPS setting, because this is mostly asynchronous transmission. So, we need to set the bit rate. Okay. So, at what rate the transmission will take place, that bit rate has to be set. Okay. In case of 8051, we have got two dedicated pins, receive data and transmit data, RxD and TxD. So, these are the two pins in 8051 that we have. So, they are again multiplexed. Okay. So, unlike 8085, where we have got these SID and SOD pins which are dedicated for this serial communication, here it is not so. Here this pin 3.0 is dedicated, is multiplexed with RxD, and pin 3.1 is multiplexed with TxD and for transmission. And there is a special register called SBUF register. So, SBUF is the serial buffer, you can say, and for transmitting any data you have to put the content into the SBUF register. So, as soon as you put the content onto SBUF register, the serial communication starts. So, you can have an instruction like move SBUF comma hash this character D. So, this SBUF will be loaded with the ASCII value of D, which is 44x, or you can say like move SBUF comma A. So, accumulator content will be copied onto SBUF, and whatever be the value in A, so that will be transmitted. You can get the copy of this SBUF into A. So, that way so you can read the content of SBUF buffer into the buffer register into the A register to see what if something has been received. Okay, and when something has been received, so you can do that. Now, there is another problem, like in case of 8051. So, this is a TTL chip. So, what happens is that this receive and transmit lines that we have, so that is pin the 3.1 and 3.0, they will give you the TTL level output. So, TTL level output means, so these signal values are in the range of 0 to 5 volt. So, it is there is some definite low and high levels. So, accordingly the signal value cannot be, the low cannot be lower than 0 and high cannot be more than 5. On the other hand, this serial communication protocol like this RS-232C type of protocol, so they have got different voltage levels. For logic high, the voltage level is minus 12 volt to minus 15 volt, minus 12 to minus 15 volt, and for logic 0 it is plus 12 to plus 15 volt. So, you see that this 8051 chip, it will not be able to provide this type of voltage levels. So, normally what is done is that we have got for serial communication interface. So, we have got another chip which is known as MAX 232. So, this left side is TTL compatible and the right side is 230 RS-232C compatible. So, so this 8051 is connected to this MAX 232 pin. So, pin number 11 of this 8051 is connected to pin number 11 of MAX 232, then pin number 10 of 8051 is connected to pin number 12 of MAX 232. Similarly, on the output side, so you can have some connector to which this is RS-232 side. So, whatever device you are going to connect, so you can design a suitable connector and do the connections there, then the signal levels will be compatible. Anyway, so once we have done these things, so we can go for this serial communication. So, this for the serial communication, whenever you write some data onto this SBUF register, it will be transmitted via this TXD pin. Similarly, whenever it receives some data, so it is there in the shift register, and from the shift register it comes to the SBUF register. So, this shift register is not directly accessible. So, this SBUF is accessible in the program mode. So, you can read the content and get it into the accumulator. So, we have to set the baud rate for this transmission and the baud rate for receiving. So, these baud rates are to be set for ensuring proper communication through the serial port. Now, for the setting of baud rate, there are some values. Okay. So, some timer, that this timer 1 has to be used for this baud rate setting, and this if you want to set a baud rate of 9600, then this TH1 should be set to -3. If you are trying to set this baud rate to 4800, then this TH1 should be set to -6, then -12 and -24. So, these assuming that the crystal frequency is 11.0592 megahertz. So, these are the various values of TH1 register that should be set for this for getting these baud rates. Now, for serial communication, so there is a register called serial control register or SCON register. In this SM0, SM1, SM2, so they are the mode specifier. So, this and this REN is the receive enable, TB8 is for transmit bit 8 and RB8 is for receive bit 8, TI is the transmit interrupt flag. So, it will be set by hardware and cleared by software. So, when this TI interrupt occurs, so then that means some transmission has taken place, and when this RI interrupt occurs, then this RI interrupt, this receive interrupt has taken place. But physically this TI and RI, so they are sending a single interrupt to the processor, and the process in the program you need to check whether the TI bit is set or RI bit is set. Accordingly, you can understand whether some data has been transmitted or some data has been received. So, we will see that. So, this SM0, SM1, so this is if it is 00, so it is a shift register mode, and then the transmit rate is fixed. So, it is crystal divided by 12, that is that 11.0592 megahertz, that divided by 12. So, that is the rate at which the transmission will take place. If you are using the mode 01, so it is a 9-bit UART, and then this the type now the transmission rate can be variable. The different baud rates that we are talking about here, so different baud rates can be selected if you are operating in the time in the mode 1 by setting this SM0, SM1 to 1. So, if you are operating, then you can set this mode to timer 1. You can use the timer 1 for setting the baud rate. If you set it as 10, then it is mode 2. Okay. So, in mode 2 we have got 9-bit timer. So, the 9-bit UART. So, there I can have say one extra bit there, and then we, so that but the transmission baud rate is fixed. So, this is crystal by 32 or crystal by 64. So, that way this transmission rate is fixed, and mode 1. So, it is 9 bit UART with the variable time variable baud rate. So, you can have this timer to set the transmission rate. So, mode 0 is the simplest one. So, let us try to understand that. So, serial data enters and exits through the received data. So, so the received data, so transmit data will output the shift clock, and so this is the thing. So, we have got this transmit data and receive data. So, this receive data is used for both transmission and receive. So, 8 bits are transmitted and received. So, LSB will be received or transmitted first. Baud rate is fixed as 1/12 of the oscillator frequency. So, this is typically used for port expansion. So, we have got so many extra bits. So, you can control so you can use these individual bits for different port as different port bits. Okay. Then mode 1. So, here 10 bits are transmitted through TXD or this or received through RXD. So, 10 bits, out of these 10 bits, one is the start bit, 8 bits of data and 1 stop bit. So, this is the 10 bit that will be transmitted, and on receive the stop bit goes into RB8 RB8 bit. Then the baud rate is determined by the timer 1 overflow rate. So, if you so timer 1 clock is 1/32 of the machine cycle. So, machine cycle is 1/12 of the crystal. So, you can find out like what is the value, like the machine cycle. So, crystal is 11.0592, that divided by 12, and that is again divided by 32 for feeding the UART clock. So, that way you can set this timer 1 value. So, this will go to the timer 1. So, this timer 1 is now getting a clock of 28800 hertz. So, accordingly you can set the timer value, okay, that for getting that delay. So, timer clock can be programmed as 1/16th of the machine cycle. So, that way, so previously it was 1/12th of the machine cycle, now it becomes 1/16th of the machine cycle. So, if you follow this formula, then you can get the delays. And whenever any instruction uses SBUF as its destination register, transmission will start. So, UART clock is controlled by this timer 1, and for setting the timer 1, you can understand that this crystal clock is machine cycle is divided by 16, and that way. So, machine cycle is 1/12th of the crystal clock, and this crystal clock divided by the machine cycle divided by 16. So, that will give you the delay for the timer. So, in mode 0, the on chip oscillator is divided by 12. So, that is the baud rate and clock. So, this is if it is in mode 2. So, we have got 2 S mod equal to 0 and S mod equal to 1. If S mod equal to 0, it is divided by 64. So, that is fixed. If it is in S mod equal to 1, so it is divided by 32. So, this baud rate is also fixed. In modes 1 and 3, so this transmission rate will be controlled by this timer 1 overflow. So, that is why these modes are useful. So, if it is connected, if it is S mod equal to 0, then this timer overflow will be divided by 32. If it is S mod equal to 1, then the timer 1 will be divided by 16. Okay, that overflow. So, that will be determining the baud rate. This way we can have different baud rate settings and different transmissions of serial transmissions of 8051. In mode 2, 11 bits are transmitted through TXD or received through RXD, and out of that 11 bit, one is the start bit, 8 bit of data, one programmable 9th data bit. So, that programmable 9th data bit, so you can use it for parity or something like that, and one stop bit. So, on transmit, this 9th bit, the TB8, it can be assigned 0 or 1. On receive, the 9th bit will go to the RB8 register, RB8 of the SCON. So, it can be the parity bit. So, this so we can compute. So, this bit is available in the, so rest of the 8 bits will go to the SBUF register, but you can get the 9th bit in the TB8 or RB8 of this SCON register. So, you can check for the parity by that, and again the baud rate is programmable by this S mod, and the PCON register is also there. We will come to that, which will control this thing. Mode 3 same as mode 2, but may have variable baud rate generated from timer 1. So, that way it is the mode 3 operation. So, this S mod is the bit 7 of the PCON register. So, PCON is the power control register. So, this is the out of that the bit 7 is the, if S mod equal to 1, then double baud rate is used. So, whatever so if you look into this diagram like here, so we said that S mod equal to 0 it is 64 and S mod equal to 1 it is 32. Similarly, here S mod equal to 0 is 32 and S mod equal to 1 is, the clock is divided by 16. So, clock is clock frequency will be higher if you make S mod equal to 1. So, that is controlled by this PCON registers bit number 7. So, PCON is not bit addressable. So, to set it, so we can do it like this. First we get this PCON register value onto A register, then we set bit this accumulator's 7th bit, and then we move this accumulator into PCON register. So, that can be done. So, this bit will get modified, this bit is now getting set for that purpose. This PCON register is the power control register. Okay. So, it has got this S mod bit. So, apart from that it has got this, so these 3 bits are reserved. So, then we have got this GF0, GF1, PD and IDL. So, GF1 is general purpose flag bit, GF0 is general purpose flag bit. So, they can be used by the programmer. Then this PD PCON.1 is the power down bit. So, if you set this PD to 1, so this will activate the power down operation. And if it is if PCON 0 is the ideal bit. So, if you set this ideal bit to 1, so it is the idle, it will activate the idle mode of operation. So, from idle mode of operation, so it will be taking out, so some interrupt should reach the processor to activate it. On the other hand, this power down mode, so if it is power down, so maybe it can advise many devices to go to power down mode and all that. So, some control signals are activated by which it will tell the external world that it is going to power down mode. So, power control is standard for applications where power consumption is critical. So, this is there are many standard for this power control, like ACPI. We have got a control standard for this power control. So, similarly, we have got 804 any processor that you have now. So, if you look into, you will find that some power control mechanism has been provided. So, this 8051 also has got this power control feature. So, this has got one idle mode and a power down mode. In idle mode, so an instruction that sets this PCON.0, it will go into idle mode, and last instruction executed before going into idle mode. So, the internal CPU, so this is the, so that will be the last instruction. So, that will be after that nothing more will happen. So, CPU clock is gated off. So, CPU will not get the clock, as a result the internal operation will stop. Interrupt, timer and serial port functions act normally. So, these operations will continue, but only the CPU will be not doing any further instruction processing. So, it will be idle, but the interrupt, timer and serial port, they will operate. All of registers, ports and internal RAM maintain their data during this idle period. So, the internal values will be stored, but will be held, but the processor will not do any other operation. ALE and PSEN will hold at logic high level, since it is the processor is not fetching any further instruction. So, this ALE is also high and this PSEN bar line is also high, to mean that no activity is taking place. Now, to come out of this idle mode, so it has to use some interrupt. Okay. So, any interrupt will cause this PCON.0 to be cleared by hardware. So, it will terminate the idle mode and then it will go to the interrupt service routine. So, that is very good, like if some event has occurred in the outside world. So, it will be turning on the processor's operation. So, it will go to the ISR, and from that point onwards, so whatever the processor was doing previously, so it will continue with that. So, the instruction which is just after the idle instruction, so the on return from the interrupt, so it will be occurring that way. So, as it is said here, so suppose this is a piece of code and this instruction is setting this pcon dot 0. So, it is setting that pcon dot 0. Now, after that, so it can come back to this point. So, but at this point the processor has become idle. So, the processor has become idle, after some time some interrupt has occurred, and when the interrupt has occurred, then this is the interrupt service routine. So, processor will execute this interrupt service routine, and at the end there is a return from interrupt, the reti instruction, and the reti instruction will take it to the instruction just after setting of this pcon thing. So, this way it can come back to this point, like it is coming to this after the interrupt is over. So, it can come to this point and the idle mode is over. So, this way interrupt can take the processor out of this idle mode and do the operation. On the other hand, this power down mode, so an instruction that sets pcon dot 1, it causes the power down mode, and the same thing, that is the last instruction executed before going into power down mode. The on chip oscillator will be stopped and all functions are stopped, contents of on chip RAM and SFRs will be maintained. Okay. So, ALE PCN bar will be held low, only reset can terminate the power down mode. So, unlike this idle mode, where the interrupts can turn off this power down mode, this idle mode. In case of power down mode, only the reset operation can be reset this entire power down mode, and it can take the processor out of this operation, out of this power down mode. So, these are very useful when we are talking about this power handling part. So, these are very much useful for designing systems where we are to save the battery, like most of the cases microcontrollers, they are used for embedded application where the battery life is important. So, we can use these processors for doing these things. So, we can say that we can put the power down, we can not require the operation. So, we can put it in power down mode and later on or in the idle mode, and whenever the service is required, we can turn on the device or turn on the services. So, this is the power control example. So, this is LJMP main. So, this is the main routine. So, you see that this is the pcon. So, pcon register we are ending with 02. So, this is this will put it in the power down mode, and and this is the idle mode. So, in the it can come back to this when the interrupt occurs. So, it can come back to this point, and on reset. So, it will be this power down will be cancelled, and this is the idle mode. So, when the idle mode some interrupt will occur, for example, here when the interrupt occurs. So, it will be doing that.